Section: Introduction. In this section, we are faced with the question of how large language models, LLMs, can accurately represent uncertainty in their output. There is a debate on whether LLMs can estimate uncertainty effectively, with some studies suggesting they can do so directly through prompting, while others argue that LLMs are too overconfident in their predictions. The challenge lies in deciding which method to use for uncertainty estimation in LLMs. One approach is black box estimation, which does not require training and can be used with models like GPT-4 or Gemini. On the other hand, white box methods require training parameters on a calibration dataset. While black box methods have gained popularity, the availability of strong open-source models like Llama or Mistral has made white box methods more accessible. Our research delves into uncertainty calibration of LLMs, aiming to improve the understanding of interventions needed for good calibration. We explore methods for achieving good uncertainties over correctness, the use of labeled correctness examples, generalization of uncertainty across different tasks, and leveraging LLM uncertainty for human decision-making. We find that fine-tuning LLMs for better uncertainties results in faster and more reliable uncertainty estimates with only a small number of additional parameters. These uncertainties also generalize well to new question types beyond the fine-tuning dataset. We also provide guidance on teaching LLMs to recognize their uncertainties using a calibration dataset. Contrary to previous work, we show that current zero-shot, black box methods are not effective in open-ended settings. We demonstrate how fine-tuning a language model for calibration can be more efficient, exploring different parameterization techniques and the amount of data needed for good generalization. Our study evaluates uncertainty estimates on questions similar to the calibration data as well as questions that test robustness to distribution shifts. We also investigate how fine-tuning LLMs enables them to estimate uncertainties not only for themselves but also for other models. Additionally, we conduct a user study to show how LLM uncertainty can impact AI-human collaboration. Section Summary. In this section, we delve into the challenge of uncertainty calibration in large language models, LLMs, and its implications for decision-making. We explore methods to improve uncertainty estimates in LLMs, finding that fine-tuning for better uncertainties can provide faster and more reliable estimates that generalize well to new tasks. Our investigation highlights the importance of intervention in calibrating uncertainties in LLMs, showcasing the limitations of zero-shot, black box methods and the effectiveness of fine-tuning approaches for accurate uncertainty estimation. Section: Preliminaries. In this section, we focus on using black box methods to estimate the uncertainty of a language model. We specifically look at methods that are computationally efficient, requiring only a single sample or forward pass. We will discuss sampling-based methods in the next section. When it comes to multiple-choice tasks, a language model's distribution over answers is like a categorical distribution because each answer choice is represented by a single token. Early studies on large language models, LLMs, like GPT-3 revealed that this distribution is often not well calibrated. However, the training method based on maximum likelihood should ideally promote calibration over individual tokens. Recent LLMs seem to show improved calibration as their accuracy increases. In open-ended generation tasks, answers are not limited to single tokens or a predefined set of options. This introduces various sources of uncertainty. The probability assigned to an answer can be low not only because it may not match the correct answer conceptually, but also because there could be multiple possible ways to phrase the answer. This makes it challenging to assign probabilities accurately, especially when dealing with sequences of tokens. For instance, in a multiple-choice test where we add a synonym as an extra answer choice, a good language model would assign equal likelihood to each choice, reducing the probability assigned to each one individually. In open-ended tasks, the challenge is even greater due to the variable length of possible answers. Adding more tokens can decrease the likelihood of an answer, even if it conveys the same idea, because longer sequences become less likely. We compare the performance of likelihood-based methods for standard multiple-choice tasks and open-ended generation tasks in our study. We use perplexity as a metric for open-ended tasks because it normalizes for the length of the sequence and is commonly used when the model provides token-level probabilities. We also explore alternative methods like prompting, which have gained popularity as confidence measures because sequence likelihood or perplexity has limitations. These methods involve using the model's outputs to create binary classifiers or sampling uncertainty estimates as text and converting them into numerical values. Calibrating uncertainties in language models by mimicking human language behavior is a challenging task. Humans themselves often exhibit poor calibration on unfamiliar tasks, and not all training data is generated by experts. Therefore, expecting black box methods to provide well-calibrated uncertainties without intervention may be overly optimistic. Alignment procedures like RLHF could help improve calibration by penalizing instances of poor calibration, similar to fine-tuning on graded data. We also evaluate the quality of uncertainty estimates from open-source models in comparison to their accuracy. Models like Llama 2, Mistral, and Llama 3 are assessed in an open-ended setting to simulate a chatbot scenario. Comparisons show that prompting methods tend to have poorly calibrated uncertainties, and their calibration does not automatically improve as the base model's performance increases. While the area under the receiver operating characteristic curve, AUROC, slightly improves with better models, fine-tuning for uncertainty still outperforms even the best base model. Section Summary. In this section, we focus on black box methods for estimating a language model's uncertainty, particularly in multiple-choice tasks where the model's distribution over answers is a categorical distribution. We discuss how maximum likelihood training aims to improve calibration over individual tokens, but in open-ended generation tasks, uncertainties arise from multiple sources, making it challenging to assign probabilities accurately. Additionally, we compare the effectiveness of likelihood-based methods for standard multiple-choice tasks versus open-ended generation tasks, highlighting the limitations of perplexity as a confidence measure and the need for alternative prompting methods to improve uncertainty estimates. Section. How should we use labeled examples? In this section, we aim to create a prediction for the probability of the model giving the correct answer. We approach this by treating the task as a simple yes or no classification problem, which we train on a small dataset containing examples of both correct and incorrect answers. There are 3 different ways we explore to represent this probability, each differing in the number of adjustable parameters and how they utilize prompts. 1. Probe. We train a small neural network on the final layer features of a large language model, LLM, that receive the prompt, question, and proposed answer as input. The network predicts the probability of correctness while keeping the base LLM fixed. 2. LoRa. Similar to probe, but with the addition of low-rank adapters, LoRa, to the base model. This allows for adjustments to the intermediate language features of the base model to enhance correctness prediction. 3. LoRa plus prompt. We frame the correctness classification as a multiple-choice task with I representing no and E representing yes. We fine-tune LoRa on data formatted in this way. By exploring these different approaches, we can investigate how much information about uncertainty is already present in the pre-trained model's features. Probe relies on fixed features, while LoRa and LoRa plus prompt can modify the model's features to quantify uncertainty. Comparing LoRa with LoRa plus prompt also helps us understand how a language-based framing of the problem impacts performance. For training, we create a varied set of samples from a selection of benchmark datasets. We use a subset of around 20,000 samples from a list of 16 benchmark datasets. We reserve 2,000 data points for temperature scaling calibration. To gain more insights into when our estimates are applicable beyond the training data, we investigate shifts in distribution between the training and evaluation datasets. We desire robustness to shifts in subject matter, question format, and the solvability of questions. Our uncertainty estimates from LoRa Plus prompt demonstrate consistent performance across different subject categories, even when the composition of the dataset differs. We also show the effectiveness of our models in assessing confidence for tasks outside the training distribution. Furthermore, we explore how language models can provide useful uncertainty estimates even with limited labeled examples. We propose two mechanisms. The model evaluates answer correctness given a question, or the model recognizes topics prone to incorrect answers. To distinguish between these mechanisms, we conduct an experiment where we replace the model's answers in the fine-tuning dataset with incorrect options. The results suggest that the model is not solely learning from error patterns in the training data. Lastly, we investigate whether a language model can not only model its uncertainties but also those of other models. Our findings suggest that uncertainties in language models are likely not specific to a particular model, allowing one strong base model to estimate uncertainties for various other models when a small labeled dataset is available. Section Summary. In this section, we explore different ways to estimate the probability of a model's correctness using labeled examples. We investigate three parameterizations: probe, LoRa, and LoRa plus prompt, to understand how pre-trained model features can be utilized for uncertainty quantification in a binary classification problem. By studying distribution shifts, subject matter variations, and question format changes, we aim to determine the generalizability of these uncertainty estimates across different scenarios and datasets. Section: Does calibrated confidence improve collaboration with AI assistants? In this section, we aim to explore how estimating uncertainty in large language models, LLMs, can help indicate the model's reliability when collaborating in decision-making tasks. To investigate this, we conducted a user study with 181 participants. During the study, participants worked on a multiple-choice exam with an LLM called Mistral 7B Instruct. Each question was accompanied by the LLM's prediction and an uncertainty estimate, which could be either calibrated or uncalibrated. Our goal was to demonstrate that users are more inclined to consider calibrated uncertainty scores when making decisions. More details about our study setup can be found in the user study section. Our discussions revolved around the debate regarding the significance of calibrated uncertainty in LLMs, how to achieve it effectively, and the potential of black box methods. Contrary to previous findings, we observed that default uncertainties from LLMs are not reliable for open-ended tasks. We introduced a set of fine-tuning techniques that generate calibrated uncertainties with practical applicability. Surprisingly, we found that fine-tuning is efficient in terms of sample usage and does not necessarily depend on specific correctness representations tailored to a particular model. This suggests that estimators can be transferred from one model to another. Additionally, we discovered that calibrated uncertainties can withstand changes in data distribution, at least in the scenarios we examined. Looking ahead, there are several intriguing avenues for future research. Currently, fine-tuning requires separate models for question answering and uncertainty estimation. Ideally, we aim to develop a unified model capable of generating questions and uncertainties without the need to switch between model configurations. We anticipate that incorporating uncertainty awareness during pre-training or alignment phases may become crucial. However, implementing such a process while preserving core language modeling capabilities poses a challenging online learning task where correctness labels evolve during training. Apart from enhancing the reliability and utility of language models, high-quality uncertainties can enhance active learning methods, such as sample-efficient fine-tuning, by selecting data points based on predicted utility and model uncertainty to balance exploration and exploitation. Uncertainty estimates can also enhance the factual accuracy of language models by favoring confident generations that are likely to be correct, for instance, through alignment procedures with reward functions that promote confident outputs. Furthermore, we illustrated how uncertainty information can influence human decision-making processes. Ultimately, as LLMs play a significant role in societal decision-making, having access to uncertainty information is crucial to prevent rare but costly errors. We acknowledge the support received from NSF Career IIS 2145492, NSF CDS and EMSS 2134216, NSF HDR 21183110, Big Hat Biosciences, Capital One, and an Amazon Research Award.